Richardson, our Vice President for Programs. He's going to be covering the principles of operation of the basic types of telescopes, reflectors, refractors, and hybrids or catadioptrics, and the relative merits of each. A little bit about eyepieces. We've got a box of them over there. Different types of mountings, equatorial and altazimuth, and some of the pros and cons of each of the types of telescopes in case you're thinking of getting one. So without further ado, Tom Richardson.
Thank you, Bill. Following Dr. Busler in making a presentation to any group is kind of like being the cattle rustler at a lynching in Texas. You're kind of the guest of honor. But anyway, we're going to completely flip-flop here. We're going to be looking at telescopes and optics. My background educationally is in psychology. I retired after 45 years of private practice, and my primary hobby interest has been ham radio. So I'm coming at it from both the psychological, physiological perception angle and the radio spectrum, electromagnetic spectrum angle. My apologies to quantum physicists. Where is our...
It's over next to the screen for some reason.
Oh, yeah. Okay. I think I punched the wrong button.
The right arrow should advance.
Ah, okay. As Bill said, there are three basic types of telescopes. There are refractors, reflectors, and your combination or your catadioptrics. I'm not necessarily endorsing Celestron, but I have a Celestron, and with my computer, their image is copied better than Orion or any of the other companies. So this is a picture of one of the Celestron refractors. We have, we have the eyepiece that you look in. There's their finder. This is an altazimuth mount. It circles in that direction, and it will also turn in that direction. This is not your preferred mount for astronomy, because to track a star, because the Earth is constantly rotating, you got to combine a vertical and a horizontal movement to track the star accurately, which makes it really difficult to stay on task there. Now, the way a refractor works, you have light waves. We're going to play like this reflector here is a refractor for a minute. No, it's another reflector. We're going to play like this is a refractor for a minute. And we're looking at that end, and we've got an eyepiece down here at this end. This is a very small refractor. You've got the objective up here and the eyepiece back here. The light rays come in from a distant object. They pass through a lens in the front and are bent or refracted, hence refractor. I hope this little demonstration will be visible to all concerned. We have a pencil. We have a pickle jar with the label scraped off, almost full of water. If we take the pencil and insert it, what's below the water level looks larger than what's above the water level. And also, it's offset. Is that visible back in the back, Freddie? You're the farthest back, so, and another one of the almost geezer society like Bill and me. The light waves come in through the convex lens. A convex lens is shaped kind of like that. As my old 8th grade science teacher used to say, there are convex lenses and there are concave lenses. And the way you remember which one is bulging out and which one is curving in is the concave lens goes in like a cave. You can also have a convex concave, which is convex on one side and concave on the other. We use these to try to take care of some optical issues that happen when we start bending light waves all around. Now, the reason that the pencil changes shape and changes direction here is the speed of light coming through the air or through space is about 186,000 miles per second. When it goes through the water, it slows down. It's like if I were still young enough to go running down the track, I might be able to make 100 yards in 30 or 40 seconds at my age. You think you can make it any faster? But that's me running through the air. Now, let's assume for a second that instead of trying to run down that track, I'm trying to run down a swimming pool. My 30 or 40 seconds has probably gone up to 4 or 5 minutes if I have to try to cover 100 yards, because the water is slowing me down. Glass does the same thing. Also, light waves are part of what we call the electromagnetic spectrum. In ham radio, we used to refer to a lot of the receivers as they're good from DC direct current to daylight in terms of their frequency coverage. When the light waves pass through the lens, they are slowed more in the center, the water's deeper, than at the edge. And the image of that object is brought to a focus point at the end. This would be like you have a lens in your eye that focuses light back onto a very, very teeny-weeny little set of rods and cones at the back of your eyeball on the retina. we can't view an image directly unless the light rays are coming in parallel. We have the lens, as I said, that focuses it back to a very small spot on the retina. Now, we can get the rays back to parallel. They're coming through a convex lens at the front, the objective, and then go through a concave lens at the back to straighten them back out. Otherwise, this would come right down, that would go right up, and they would cross. This is what Galileo had to work with. It'll work, not very well, but it'll work. He contributed a bunch of pretty good stuff for us. One advantage of the old Galilean type of telescope, like you use in a refractor, instead of its being back here at the back where we're looking up the telescope or up the telescope, we insert the lens, that eyepiece or ocular, into the focuser. I'm not going to try to jam this in.
Run it out some.
This isn't my telescope. Anyway, that's okay. Yeah, that's why I've got my hand under it. And we adjust the focus so that the light is focusing off the secondary mirror, or in this case, it's a prism.
Well, it was a prism, but it's coated on one side.
Oh, okay.
It's actually a mirror.
Oh, okay. You can do it with the prism. A finder scope is a real necessity. I learned this, unfortunately, very hard way at our picnic. Gentleman and his wife and 2 kids came up and said, "We've got a new telescope and we don't know what to do with it." Well, okay, yeah, sure, I'll help. It didn't have a finder scope. It was in a little box about yay big. You could actually see the moon and the craters with it, but the only way to find anything with it was to bore sight it like you do with a rifle, looking up the telescope at your target and moving the scope around to where it was. What your finder scope does, it's got a short focal length and it gives you a fairly wide field of view. You find your object in that, center it, and you have it lined up, hopefully. If you don't, you've made a big mistake. So that what's centered in your finder scope is also centered in your telescope. And we can find our objects that way. They make all kinds of finders. Most of them, my favorite kind, are small telescopes because I can see a little bit better, even through our light pollution here in Bartlett and Memphis. And the other kind projects a little red dot that you line up on your target. And these are much easier to make, much less expensive, and I never could get mine to work very well at all. One of my many mistakes in purchasing astronomical equipment. A variation on the reflector is what we call the Cassegrain. We have, with the Cassegrain, a reflector telescope, a secondary mirror, but the light from the secondary mirror, instead of focusing out the side, is focused out the back. That's a picture of one of the Celestron Schmidt Cassegrains. We have a corrector plate on the front with a mirror right in the middle. The light comes in, hits the mirror, bounces back up to the secondary, then back down to the telescope. So boy, we got a long focal length that way. Focal length is very important. We'll get to that in a second. The catadioptric uses a spherical mirror similar to a reflector, a regular reflector mirror, but with the corrector plate over the front so that you don't get a lot of chromatic aberration and other visual distortions. You have a convex secondary mirror, meaning it's bulging out. It's not a concave like on the back, that sends light back through a hole in your primary mirror. So you're losing a little bit of aperture there. Not much, but a little bit. But the neat thing about the catadioptric is it's got a very long effective focal length. Why is focal length important? Your focal length basically, along with the focal length of your eyepiece, is what determines the magnification of your telescope. When you see a telescope advertised, and it's advertised as it's 400 power, run like you had a mad dog after you. It's worse than the new lawyer commercials where the guy is smiling and says, "Here, we'll give you $2,000 because of your auto accident." Stay away from those people, those things. That's a sure sign when they talk about the power of your telescope as the primary reason to buy it. Read that as D-O-N'-T. Don't. Now, the power of your telescope, how many times the image is magnified, is the focal length of the objective. And whether it's a refractor or a reflector, it's the same thing. The focal length of this telescope is from the mirror back here up to where your secondary or mirror or diagonal is. The longer your focal length, usually the more power you can get with your telescope. Your power is determined by the focal length of the objective divided by the focal length of the eyepiece. if I'm using a 20 millimeter focal length eyepiece in here, and I change over to a 40 millimeter focal length eyepiece, the image is going to be about half the size. We adjust power by changing the eyepieces. The shorter the focal length of the eyepiece, the higher the power for a given objective. Bill made these slides up, and I am appreciative of that. Let's say that our telescope has a 48-inch focal length mirror and is used with an eyepiece that has a half-inch focal length. The power of that telescope would be 48 inches divided by a half inch, or 0.50 inches, would be 96 power. In other words, something is going to look like you're 96 times closer to it, or it's 96 times larger than it would look to your naked eye. Magnification is theoretically unlimited, but there's a practical limit of about 50 times per inch of diameter, whether it's a refractor or a reflector, lens or mirror. Most of your observing, you're going to be doing at far less than your maximum magnification. I have a really good Orion Plössl eyepiece that I caught on sale that I very rarely use because it's 6 millimeter focal length. And even in 11-inch catadioptric, I've got to be in a very dark spot with very transparent skies to be able to see anything clearly with it. My most used eyepiece is a 20 millimeter, and my Schmidt-Cassegrain has a 2800 millimeter focal length. Mark has one a little bit bigger than mine, and what's your focal length, Mark?
It's an F10. I'm not
Yeah,
sure millimeters what that is.
they're both F10s, but if we have a 2 1/4 inch refractor, that means that the objective lens is 2 1/4 inches in diameter. It's got a maximum useful power of 2.25 times 50, or 113 times. Now, we've talked about the focal length of the telescope. Let's talk a little bit about eyepieces. They come in very different designs, and each one has some pluses and some minuses. Amongst the things that you got to consider about an eyepiece is let me back up on that. One of the things you got to consider about an eyepiece is well, let me back up again. Your focal ratio is just like in a camera. The focal ratio is the focal length of the objective divided by the diameter of the objective. If we got an 8-inch mirror reflector with a 56-inch focal length, the focal ratio is f7. Now, lower f units, they refer to them as being faster. When they have the same diameter, give you a wider field of view, but a lower power with the same eyepiece. It doesn't give you any additional brightness because only so many photons are bouncing off that mirror or coming through that lens, regardless of how far it's got to travel within the telescope. These telescopes are shorter with higher f ratios and therefore are somewhat easier to handle and transport. I've got a great telescope. I love my CPC 1100. One thing that I don't love about it is in another 4 or 5 years, good Lord willing, the creeks don't rise, I'm not going to be able to carry the thing. I'm not going to be able to set it up. The thing weighs 65 pounds. Mark and I have been doing some observing together. He's got a 12-inch Meade Catadioptric. It's a tank. Fantastic telescope, but it's a tank. It takes Mark and me both to get it out of his car and get it set up on the tripod. And my little 11-inch Celestron, I can pick up, but it's 65 pounds to set up onto the tripod. And that's one of your real disadvantages of the Catadioptric. They're built like the Bismarck and weigh just about as much too.
That was 25.
Yep, I envy you. One issue with an eyepiece is what's called the exit pupil. And this is the diameter of the parallel beam of light rays coming out of your eyepiece. Now you don't want your exit pupil to be bigger than what it's got to go through, namely the pupil of your eye. When you're a nice young person, you've got about normal lighting conditions, your pupil's going to be about 7 millimeters across. When you get to be a stargazer and you've used your eyes a long time, it ain't that big anymore. But you want to get your light focused from your eyepiece to where it is focusing through ever how wide your pupil will dilate at night. The exit pupil is the diameter of the objective divided by the power of the telescope. It shouldn't be greater than about 1/4 of an inch, 7 millimeters, or you can't see it all. I know on a couple of my eyepieces, it's kind of fun to use like a 40 millimeter or a 20 millimeter focal length because I can, when I put my eye up to the scope, I can look around. It's kind of like looking at different parts of your TV screen. What you don't want to do is have an exit pupil that's too big for your eye. That's what we refer to as the minimum useful power. It's the diameter of the objective divided by 0.25, or 4 times the diameter. With an 8-inch telescope, the minimum power would be 8 times 4, or 32 power. If you got a longer eyepiece that wouldn't give you that small an exit pupil, you'd be wasting a lot of what you're trying to look at, because it would be hitting the pupil, the iris of your eye, rather than the pupil. Remember, the maximum power of this same telescope is 8 times 50, or 400 power. That's the maximum power. Another thing we need to look at is what's the limiting magnitude of a telescope. We describe the brightness of a star in terms of magnitude. Polaris is about 2 magnitude. What your telescope will resolve, what you'll be able to see on a good, clear, ideal night, the magnitude of the star is 9 plus 5 times the logarithm of the aperture of the telescope in inches. 8-inch telescope, limiting magnitude 9 plus 5 times the log of 8, or 13.5. On an ideal dark night, ideal dark sky, as you're in the middle of the New Mexico desert, very low humidity, no light pollution, you could see with this telescope here something of magnitude 13.5, which would, you can, on a good dark night, in a good dark sky, a clear sky, low humidity, I think the human eye can get up to about magnitude 6. Now, there are a couple other things we need to think about with eyepieces. One of the issues that we have to consider is the field of view that we want. What do you want to look at? Do you want to look at part of the moon? Do you want to look at all the moon? Do you want to look at a specific crater really, really big, really up close and personal? Do you want to look at a nebula? Do you want to look at another galaxy somewhere? That's all determined by the field of view. And on an eyepiece, when you buy it, it's going to have, the manufacturer is going to specify the design, how the lenses are arranged in it, whether it's an Urfel or a Plössl or a orthoscopic. It's going to specify the focal length of the eyepiece and the apparent field of view, and most important, the eye relief, how far back your eye has to be from the lens of your eyepiece. Your actual field of view, and this will be expressed in degrees, is the apparent field of view that's specified by your manufacturer, and it's dependent on the type of eyepiece, divided by the power of the telescope. So if we've got an apparent field of view of, let's say 50 degrees, and the power of the scope is, that we're using is, let's say 400 power, we would have 50 divided by 400, and that would give us the fraction of a degree that we could actually see would be our actual field of view. Anybody got any questions on eyepieces before we move on to the last part on the mounts?
I ask you this, that company you mentioned, called Edmund Scientific. We bought some stuff from him, and they seem to be real good with the stuff they put out.
They've got a really good reputation, I think. I think Bill has been in it longer than I have, and he's got an Edmund Scientific.
Well, they don't make this or a lot of telescopes anymore. They're mainly scientific gadgets and things now. Their astronomy is fading away now.
Your big three in the U.S. telescope market, and most of the telescopes are made in China or Japan, are Meade, Celestron, and Orion. And Mark has a Meade. I've got a Celestron. Tim Harris, our treasurer, who's not here tonight, I think has an Orion Dobsonian. And they're kind of like General Motors, Ford, and Chrysler. They're your big three. There's some more that put out telescopes, but your big three are Meade, Celestron, and Orion. And both Celestron and Orion have a weekly newsletter that has all kinds of really neat astronomical stuff in it. You can sign up for it, it's free, and they also send you all kinds of sales stuff and wonderful stuff like that. I bought some observing goggles for $2 a pair that are normally 10 because I signed up for the newsletter. And they are all the time having all kinds of neat sales and stuff like that, and they've got some regular star charts and all kinds of other really useful information. But back to mounts. There are two types of mountings, an equatorial and an altazimuth. There is a third type that is a variation of the altazimuth called a Dobsonian that sits on the ground, and you can get a huge telescope, very mobile, but they're a bit difficult to guide and get pointed right where you want them. But it's a good way to mount things. With your equatorial mount, you have to line it up so that your equatorial axis is looking at Polaris or just a little bit off of Polaris. It has to be polar aligned. But once you get that done, the telescope will track a star by moving in only one direction. You don't have to worry about two directions at once like you do with altazimuth mount. There's a picture of an equatorial mount. I'd pick this up, but it's Bill's telescoping. Can y'all see it from? Okay. One of the biggest things you have to be concerned with any kind of mount is the stability of the mount. If you've ever tried to use a pair of binoculars and you think, you're looking up at the stars and everything's jumping all over the place, the movement of the binocular magnifies the movement of what you're looking at by the power of the binoculars. So, same thing with the telescope. I bought a couple of cheap telescopes a long time ago, and the mounts were very flimsy, and it just drove me nuts. Somebody could sneeze in Fayette County, and my telescope would wiggle in Bartlett. It was just about that bad. I bought it on Home Shopping Network. That's before I started getting serious about astronomy. With an altazimuth mount, it moves in two directions. This is a picture of my telescope, the CPC 1100. We see it's got the big forks on it, the telescope, catadioptric, finder scope. It rotates around a horizontal axis and it rotates on a vertical axis. Now, this is a motorized telescope. It's got a computer in it that will point it at whatever you tell it to point to. It's kind of astronomy for dummies, which fits my case perfectly. But it's, when you're observing with an altazimuth mount, with mine that's electrically driven, and Mark's is electrically driven, you hear those little motors just running and running and running, and you hear both the vertical axis motor and the horizontal axis motor trying to move the telescope in both directions to track your star. This is, like I say, extremely important. Whatever mount you use, it needs to be sturdy. One trick you can use if you've got a telescope and your mount's not sturdy enough, get you a barbell plate or something fairly heavy and hang it from this part here. That gets the center of gravity much lower and dampens vibrations wonderfully. A little trick. Relative merits of the various types of telescope. Refractor, no, you don't have to worry about alignment with it. Once they make it, it's made. They're pretty expensive to get good quality glass, and they're best used for bright, small objects like the moon, planets, double stars, and stuff like that. The reflector, like this, frequently needs alignment. You jiggle it a little bit, bump it, it falls over and doesn't break or anything, and it's out of what we call collimation. And you have to realign your mirrors so everything is coming and going exactly where you want it to. Your mirror is probably going to degrade over time. That's something you don't have to worry about with the refractor. Your lenses would rarely degrade. You'd have to do something really ugly and nasty to them, like clean them with a wire brush. Your reflector is really good for really dim objects like your nebula, galaxies, star clusters, Messier objects, things like that. The catadioptric, Schmidt-Cassegrain, you can get a large diameter, a very long focal length because the light's bouncing so many times, and you have very high power, very bright images. It's good for all types of observing. Drawbacks: if I were 35, there wouldn't be any question in my mind what to get. Catadioptric, coming and going. I bought a catadioptric at 70 years old, which wasn't the smartest thing I've ever done. They're pretty expensive. A lot of them are not really well configured. You can basically count on Celestron, Meade, and Orion to take care of any technical issues that you have with your telescope. And another real drawback to your catadioptric is you've got this corrector plate on the front. Remember that. What's going to happen on a night like tonight? 5 minutes? 10 minutes? What happens when you open your car in the daytime and turn on the air conditioner? Lots and lots and lots of dew. We've got what's called dew strips. They're little electrical heater elements that you put around the objective of your Schmidt-Cassegrain to cut down on that dew, but with a big scope like Mark's 12-inch, Rick's 13, my 11, even that dew strip doesn't always get all the dew off. So I've got a little El Cheapo Supreme 12-volt hair dryer that, hey, it works, that you'll see me standing in front of the telescope getting the dew off. Like when you take a shower and your bathroom mirror is all fogged up. Same principle. And that's it. Thank you. Anybody got any questions?
Thank you, Tom. Now is our chance. If you have any questions about telescopes or what to do next, you can ask now, or even better, come to our observing sessions, bring whatever telescopes you have, look through ours. We're show-offs. We want to show you stuff through our telescope. Every object looks different through every telescope. You just go to an observing session, it's like going through a buffet line. Just look at the same thing with different telescopes.